Good morning, everyone. It's a pleasure to be here. That's a first lecture of on the fundamental section, theory and background. So it's on dynamics. Yeah? So I'll need to embed it in the context of whole brain dynamics, and of course I will do that. What I will do is I will go systematically, so it's educational, systematically through some of the key concepts. Not too mathematical, but still linking it to mathematics. That's relevant, specifically to the type of mathematics and the concepts you need in whole brain modeling. So we will have neural mass lectures, we will have lectures on whole brain modeling, networks, etc. So this is a language that I will provide you with. And there is one key concept I want you to get across. Dynamics can be understood geometrically, on the one hand side, plus linking the geometry to vector fields, because there is a time evolution. Dynamics implies time evolution. And the way we define it is every system is defined by a set of state variables, and they span a space. Yeah? And as time series evolves, what we are having is a trajectory that is being traced out in this state space. Yeah? And if the dynamics is low dimensional, and everything that is systematically reproducible in a coherent fashion is typically low dimensional, there will be a reduction on a lower dimensional state space. Yeah? This reduced state space we call a manifold. Yeah? Very often it's a surface represented as a surface. When it's higher dimensional, we talk about a hypersurface. And then this trajectory has a directionality. These are the arrows. They are going to the manifold. Yeah? This is what it means that the system is lower dimensional. And then they are doing something on the manifold. Yeah? The trajectory evolves. And this is the object that we wish to understand. There is a geometrical aspect, yeah, spanned in space, and a flow that we describe typically by vectors. Yeah? And we're going to step systematically through this. Every data set that you're looking at can be described or should be described in terms of this type of language, because when you're applying metrics to quantify it, it's a quantification of this object that you see here. This is a lovely example from Brennan project that I like actually very much. This is C. elegans. This C. elegans empirical data, measured data of neuronal activity, but also of behavior, and it's also simulated data. And what they did essentially, the physical motion, the movement of the C. elegans, yeah, which is a type of a worm that is making locomotive movements, and maybe oscillatory or bounding movements, and this can be represented. This is a time series that you see to some degree represented here. You can measure the neuronal activity, and then using some dimension reduction methods, such as PCA in this particular case, you can actually reconstruct the individual trajectories, and then you need to estimate the manifold that is represented here, and also the flows. This is what you have here. Yeah? This is, in this case, the activity of the neurons. This is the key object we are interested in. When you're performing functional connectivity analysis or some statistical evaluations, what you're doing at the end of the day is you're mapping some type of other objects that you can actually, not other objects, but some parameterizations. Functional connectivity is, for instance, covariance. And a covariance matrix is nothing else than an ellipsoid. So you're fitting actually an ellipsoid to this, whether it's appropriate or not. But this is what you're doing mathematically, and you're aligning it with the major axis. But at the end of the day, all the detail, the ground truth is this object. Not just the geometry, not just its topology, but also the flow. And that's what we have to go through and will unpack. And we are going to do this step by step. So, we start with a one-dimensional system, yeah? And we're going to spend actually some time on it and address every single concept. A one-dimensional state space, well, you have only one single variable, let's call it x, and if you have only one single state variable, then the state space is one-dimensional, obviously. Yeah? And when it's one-dimensional in this state space, you may have areas in which once the trajectory is there, it does not evolve. We call this a fixed point, or a stationary point, a fixed point. This is represented here and represented there. Yeah? Which means when you're not on the fixed point, then it's not a fixed point, which means there is a flow. The dynamics evolves here. In this case, from this fixed point, the dynamics goes to the right or to the left. We call this an unstable fixed point. Because the flow directly on the fixed point is zero, in its neighborhood, it must be slow. There is no alternative to this. Yeah? Same thing here. Now you have two areas of this space, here and here, where the flow is slow, which means, in general, the flow will be fast here, because it will be different, so it will be faster. It will not be slower, because here the points with the zero flow are here and there. So that follows very naturally out of the organization thereof without doing any mathematics. Same thing here, fast going towards this fixed point. Stable fixed point, because everything is attractive. Unstable fixed point, it's not attractive, it repels. This flow structure we can describe mathematically, and this is all we are doing in dynamics, and we can describe it in different fashions. We can describe it in words, we can describe it mathematically, we can describe it by plotting all possible time series as a function of the different initial conditions. What we typically do in whole brain network modeling, we use differential equations. What this means is we have a time differential here, so this is derivative of time, equals some nonlinear function, depending on the state and depending on its control parameter. Said differently, this is a rate of change, so I need to define an initial condition, let's say somewhere here, and then this, the differential will tell me I have to go to the left. And I will have to go to the left fast, because I start here, so f must be large and negative, so I'm going to the left. Yeah? What we are doing as an experimentalist, we are actually parameterizing this. This is our biophysical reality, parameter k. Yeah? So it can be excitability from outside, medical, interventions via drugs, etc. Yeah? This is our system. Now I can link this expression to that very simply by adding, I'm not adding another dimension to the system, it's a dummy extension, but it's the x dot, and everything I just described in terms of this f is actually represented here. Look at this. In the example, what I said is if we start here, it goes to the left, assuming x grows to the right, so it must be negative. It must be negatively fast, so big negative number. Here, it must be zero, because it's a fixed point, 0, 0. And here it must be positive, because it goes to the right, same thing here. We just connected nonlinear dynamics to this description of the flow on this one-dimensional space. Nonlinear, because this is not just a straight line, it's nonlinear. If you can approximate this, for instance, by a parabola. Yeah? This goes back all the way to Poincaré, about 150 years, plus minus, a little less, yeah, ago, so linking geometry and flows. Oops, pardon. Yeah, and this is, I will show you some examples here. So don't forget, it's a one-dimensional state space, so the dynamics lives here. This is just auxiliary for us to describe that. Concrete example, x dot equals sine x, this is a sine function. The system lives here. Fixed point, fixed point, fixed point, infinite number thereof. Flow positive to the right, flow negative to the left. This must be an unstable fixed point. Yeah, so you see that the slope here is positive. When it's negative, it's always a stable fixed point. This is the situation here. So we can if I want to plot the same system, right now I'm replotting it here, the corresponding time series are here. This is what you typically see in experiments. X, 0, corresponds to this point. Stable fixed point, this is a pi, is here. The time series are here between these 2 points. It depends on the initial conditions. You start slowly in this neighborhood, slowly, fast, slowly, which means shallow onset, slope, steeper, and slow approximation, pi here. This is identical. These are 3 ways now to describe the same system, through time series, through the flow, through the mathematics. And these are typically the 3 ways of how we are doing it. And I'm showing you some different examples now. That's what I'm going to do for the rest, and then some applications. Stable fixed point. This is now a parabola, unstable fixed point. Plotted here. This is what we are seeing. Yeah? For k negative, if I increase k, what does it do to the parabola? It shifts it upwards. Yeah? Then these 2 fixed points starts going closer to each other. Once they do this, the parabola moved upwards. It doesn't intersect anymore, so actually the flow goes all the way to the right the whole time. I can also put it directly at this point where the left and right fixed point collide into each other. We call this a bifurcation. K equals 0. In this case, the flow goes here, fixed point, and then over there. So this is one of these exotic, extreme cases that we have. And so as a function of k, I go backwards. As a function of k, in theory, I go backwards, yes. As a function of k, I can actually change what we call the fixed point skeleton. 1, 2, so I'm parametrizing the flow, I'm parametrizing the system, and I'm changing its behavior. I can collapse what we just discussed for the different various values and the different time series. I can collapse into what we call a bifurcation diagram. K is being plotted here. And X, I'm just plotting the positions of the 2 fixed points along this axis. The unstable one is here as a dashed line, here. Stable is below. And as I increase the K, so I go from here to there, the 2 fixed points get closer and closer and closer and then disappear, yeah, at this point. This is a bifurcation point. With this, you have actually already the majority of the concepts that we need in 1 dimension. When we are going in higher dimensions, the same thing happens. It just becomes more complicated, richer, more complex. We can get oscillations in 2D. If you have an oscillatory system, you must have 2 dimensions. If not, you're missing something. Yeah? And in 3D, the manifolds can become more complex, folded in space. Here you see a 2-dimensional cylinder spanned in 3-dimensional space. Yeah? We can, in a nonlinear system, here in 2D, as you saw, we can have multiple fixed points. And here you have an example for 2 fixed points, 1 and 2 in a 2-dimensional system. So I have 2 differential equations, and the flow is not constrained to the 1 dimension anymore. It's 2 dimensions. So I have a vector field. And in this case, I have 2 stable fixed points. And an unstable fixed point, actually a saddle point, because the flow goes from here to there. So it separates these 2 regimes. Yeah? Geometry. Yeah? Or topology, yeah? Both in this case. Yeah? One aspect that is important, nullklein. Nullklein is the following. I set the first equation to 0, which means I'm looking at areas where the flow in the horizontal direction is 0. We call this a nullklein in X. Same thing for Y, that's a vertical. Yeah? So these are the 2 functions here. Where they 2 nullkleins intersect, it gives us a fixed point. Always. Yeah? Whether it's stable or not, different story. We don't know. This needs to be tested. Here you have, on the second example, so this is bistability, something we run into all the time in neural masses. And another one we run into is oscillatory behavior. And this is a famous bifurcation, a Hopf bifurcation. You need 2 dimensions, as I told you. And the big difference to 1-dimensional system is you can actually rotate in, and this gives us an oscillation. Yeah? And I can change the stability. Here I call the stability parameter A. And if from stable fixed point, it becomes an unstable fixed point. So we may run into this discussion of Hopf bifurcations also. So just to give you, to orient you, where do I have to point you? To you guys? Yeah, apparently. Yeah. Where's the antenna? Yeah. In one dimension, you can have only 3 bifurcations, a little variance of, nothing else. In 2 dimensions, there are more. Yeah? The relevant ones for us are Hopf bifurcation, saddle node, and homoclinic bifurcation. Yeah? So this gives you a little bit of feeling for the numbers we are running into. Yeah? Here is some reading that I recommend. This is very basic introduction to nonlinear dynamics. I think there is an updated version. In depth, Arnold was a mathematician who did excellent work, actually, and it's a wonderful book. Pattern Formation by Hermann Haken. Yeah. This is a book in which Michael Braxby, who is the speaker here, and I have actually a chapter in there for Introduction to Nonlinear Systems, using very much the same language as we have here. So I recommend that also. Yeah. I have difficulties with this thing here. Thank you, but let's, yeah. So let me put this in the use of the system language that we just wanted to develop here. Yeah. So in higher dimensional system, now going beyond 1 or 2 dimensions, we can have the same situation, but in this case now it's Q is a vector, so there can be m dimensions as you see represented here. All the concepts are the same. The manifolds can be more complex. You have bistability, fixed point to the left, limit cycle. We call this when it oscillates. Yeah. And the other concept I want to get across is, John, I have 40 minutes, right? Yeah? Because this thing here says 20. This is a little disturbing, but it was 40 minutes. I'm feeling rushed. So. Yeah. Okay. Good, then.
We'll take 1 or 2 questions.
Good.
We'll take 1 or 2 questions straight away.
Yeah.
And then we'll have time for a second round of questions after the 3rd talk.
Good. Then don't feel rushed, and thank you. Yeah, so let's relax, slow down. This is a manifold with a structured flow on it, etc. I told you, key objects. This is a mathematical language of what we want to understand. Yeah. So, how do they get generated? And there are different ways. And historically, when you go back in the history of pattern formation, we talk. This here is nothing else than this is a higher dimensional space. And this is the dynamics. We talk about spatiotemporal dynamics. These are waves that organize themselves. Joanna will talk later, I assume, about wave organization, stable propagating waves, etc. This is a language to describe it. And because it's not fuzzy, incoherent, it must be low dimensional. You just need to find the right projection into the right subspace. This is the object that you're after. Hermann Haken, that I mentioned earlier, he has systematically formalized this, and one of the means to do this is when you're close to these bifurcations that we discussed. Yeah? So qualitative changes, yeah, from one state to the other. This was when the topology of the flow changed, or in the examples we discussed, it's a number of fixed points that changed. Yeah? Under these type of conditions, you always have the emergence of such a low-dimensional object. Always. It cannot be any other way. Yeah? That's a local center manifold theorem. Yeah? And that means, in order to have this, you have to operate in the neighborhood of these bifurcations. Laser onset of very laser, yeah, of coherent light is an example. Yeah, superconductivity is another example. There are many examples in life, in biological systems. Yeah? So, pattern formation, etc. Another way to do this, not necessarily in the neighborhood of this type of critical points, bifurcations, is symmetries. As a symmetry, and I'll enter into more details on this, a symmetry means that you can actually map one solution of the system upon another solution. Or said in different words, if there is rotational symmetry, the system behavior does not change when you perform the rotation. A rotation, for instance, is a continuous symmetry, so you can actually map it from one angle to another, you rotate, and the system behavior does not change. Yeah? You can exploit this actually, and this is called equivariant dynamics. Yeah? So for dynamic systems with symmetries. The way we formulate it mathematically is the following, is exactly what I just said. You have the system dynamics Q, yeah? And you perform a symmetry operation, and it maps the system back on itself. There are some, what we call group theory, when you perform this type of operations. The key part is that this symmetry translates in invariant subspaces. It's intuitive because, as we just said, you map it on itself. Which means when you are in state space, and imagine you have a hypothetical area, subspace in state space, and you go from this point to that point on this manifold, then the behavior does not change. And if it's actually a continuous symmetry operation, as like in the rotation I said, this entire surface must be the same solution by definition, by construction. Yeah, so whenever you have a continuous symmetry, let me say it explicitly, whenever you have a continuous symmetry, you're creating an invariant subspace in this state space. Yeah? One symmetry condition could be, for instance, imagine a network. We're connecting to whole brain networks. Yeah? And we have fully symmetric coupling. Let's call this symmetry condition mu. And under this condition, whenever you go from one node to the other, if the nodes are non-distinguishable, they are identical, and the connectivity, imagine a fully unconnected system, or all-to-all connectivity, under these conditions, you have a symmetry, a condition that you can impose. And if the network is very large, it's quasi-continuous. Yeah? Under this condition, you can actually write that the connectivity equals omega 0, constant, all-to-all, or unconnected if omega 0 is 0, plus some symmetry breaking. And now you can actually take some what we call perturbation theory in nonlinear dynamics and take this very not yet defined dynamic system and perform some expansions mathematically, in which we are not going to do, but I want to show it to you, where you make an expansion in the neighborhood of this symmetry. You get two terms in the neighborhood, and the first term is a manifold itself, the geometry, and the second one is a flow that is being generated on the manifold. Actually, look at this term. Let's break this coupling here. When we do this, if it works or not. Is there a way I can move it here forward? Yeah, thank you. Mu not equals 0, so I broke the connectivity, the symmetry in the connectivity, and then previously the flow was 0 here, and now we're generating a flow, like a multi-stability, one fixed point, another fixed point, a circle, etc. You can show that this is true for any system with symmetries that you can formulate in this particular form. So this is very abstract and very general, but it's good that it's general because it allows us actually to apply it now to a whole brain network. Maybe that's a better way of doing it. Let me become very explicit. Two-dimensional system, x, y, state space. If fx equals fy, you can demonstrate that you can always map it on coordinates such that you have a circular invariant subspace, fully symmetric, and this is composed fully of fixed points. Now, these fixed points, no statement is being made about stability. Yeah? This is determined by the parameters in here. But if this invariant subspace is unstable, then you go away and the story is over. Yeah? If it's stable, you get attracted to this, which is good. So you get attracted to this, and once you're on the manifold, nothing changes. So if you break this symmetry, then by definition, the two null clients are not on top of each other anymore, so they are slightly different. There will be some intersections, such as here and here, yeah? And some areas where they're close to each other, but not intersecting. What does that mean? They're close to each other, but not intersecting. The one null client is x dot equals 0, horizontal flow 0, and y dot is a vertical flow 0, which means we have an area here that happens to be attractive on the one hand side, and where the flow is slow. Outside thereof, it's fast. So for the first time, what we are running into is a timescale separation. It's attractive, it collapses fast on this manifold, yeah? And then there is a dynamics that evolves along the manifold. What type of dynamics, we don't know, but here I'm saying it's going from here to there. Wonderful. And then this makes it an unstable fixed point and a stable fixed point. In simulation, this is what it looks like. Two-dimensional system. This is symmetry breaking. Mu equals 0. We have the sphere. And time series being plotted. Here I call it U and S, just for a little variation. Yeah? U and S. And this is a manifold. These are the intersecting points. So we have multiple thereof. Let me start this again. So it's being attracted fast, so you see it goes very fast, and then it evolves slowly along the manifold, exactly as we said. Very basic general behavior. Yeah? That's nice. We just generated our first structured flow on this manifold. If we add noise, the following is happening. Let's add noise, whatever noise it is, and then the following is happening. It goes to the manifold, and it's actually sampling the manifold, sampling the geometry, the unfolding of the manifold and the flow. Most of the time around the stable fixed points, it's sitting, but it's sampling the geometry of the flow. This is a type that we are seeing. We have a data cloud that is constrained to a lower dimensional subspace that we are sampling. Yeah? And there is a flow. Here in this case, the simulation went only to a one-dimensional fixed point. And this is the corresponding dynamics that you see here. Yeah? But now we sampled only this one flow. If I had initiated it somewhere here, then we would have had other realizations. This is the story behind that. Now we can do the same thing with higher dimensional systems. For instance, on a sphere. In this case, n-dimensional. I think it was 20-dimensional when this simulation was done. Yeah, 20-dimensional. The manifold itself. Can you say it from just looking at it? What the manifold? Yeah. Well, you can read. Yeah. So it's a sphere. It's a spherical hypersurface attractive manifold, and we have two stable fixed points there. And here I can plot in the sphere, and you see the same dynamics. So it's a two-dimensional manifold on which this dynamics is constrained by stability. Yeah? But the system itself is 20-dimensional. Yeah? So, and these are some of the concepts I wanted to share with you. Here is some further reading, the neuron paper. Here, more of the mathematics you find in there in terms of equivalent dynamics and invariance. And this is with applications to neurosciences. So let's take these concepts now and carry them into the whole brain dynamics, as John was telling you about, and I would like to apply it to two situations. Resting state dynamics and epilepsy. Epilepsy as being the primordial, prototypical dynamic disease where dynamics expresses itself through the organization of the seizures. Yeah? But first of all, whole brain modeling, since this is the first lecture, just a quick words on that. Yeah, the way we build these whole brain models, we use non-invasive brain imaging data, topography, topology. So out of this, we can build a network. Topology, connectivity, topography, organization in space. The dynamics typically looks like this. This is the neural mass dynamics, of which we will hear more. Psi is a vector, so we have a vector field at location x. X is now not a variable, but it's a position. Nonlinear dynamics is exactly what we discussed. This is if we have intracortical connections, the connection term, and here we have the white matter connectivity that comes from the connectome, typically with time delays associated. So when we take this situation and start simulate it, yeah, then what we are seeing is spatiotemporal dynamics. Yeah? When we want to quantify it, we can compute functional connectivity. Functional connectivity is, depending on how you do it, covariance between the behavior dynamics of the individual brain areas. Yeah? And these are the regions, so 80-something regions. So this is the covariance. But you see, what we are doing is actually we are windowing it, so you see it actually changes. And this has become known now for 10 years that the functional connectivity dynamics is actually has a time scale of change. And this is often referred to as FCD. And here I'm plotting the cross-correlation of functional connectivities as they evolve over time. And what you see is actually you have this characteristic square structure, yeah? So you have areas, this is in seconds. So if we look at bolt signal, for instance, this here is about 100 seconds. So this is minutes time scale where the covariance, the cross-correlation between subsequent functional connectivities does not change, yeah? So these patterns are characteristic, and if we look at them, if we now project it into the relevant subspace, what we are seeing here is actually the manifolds that we just described about. Yeah? So here, this is first principal component, second, and as we are in one of these squares here, we are sampling part of the manifold, and then it reorganizes itself when you go from one square to the other and to some other part of the manifold, sampling it. Yeah? So there is a dynamics behind it, not sampling always the entire manifold by in its completeness. Yeah? So depending on where you are. This is actually very useful. Here you have an example, for instance, from aging. This is a functional connectivity dynamics as I just showed you for a younger subject, 18, for still young subject, 56 is a very good age. Yeah? So, yeah. And then a little older person, and you see that actually we refer to this just by visual inspection. You can already see it's less fluid. There is less flexibility in the brain organization. The squares are bigger, which means you're hanging out on the same parts of the manifold for a longer time. Yeah? This is a form of dynamics that with a manifold that can actually describe this. This is metrics that is being used to characterize it. What is behind that are the manifolds and the structure flows on it, as we discussed it. We can actually do this systematically. I put it back into the whole brain network concept. This is psi. If we set, ignore this part because we don't have this here. If we set G equals 0, then we have very small G values here, G. So nothing is happening until then. And this is a corresponding functional connectivity dynamics, FCD. It changes a little bit, but then here it completely reorganizes. This is what I just showed you. And this is the type of, we find in brain imaging data, this checkerboard structure in the FCD with the fluidity. If you are off this working point, you lose much of the fluidity. And as we see in aging, this is one of the elements that is happening. Can you tell me what the manifold looks like for this here? Yeah, any idea? Close to the symmetry, we have multiple hundreds of nodes, and there must be a translational invariance, etc. What does a data cloud in the space look like? Yeah? Yeah, you're making some funny movements. What does that mean? You want to say something? Just fixed points, but that is the dynamics. What does a geometry look like? It's invariant, and it's all identical because the connectome did not do its work yet. Yeah? In this project, it's spherical because it's invariant under the rotation. And what we are having here, it is fixed points, you're perfectly right, and actually up and down states, but it's a projection in a lower dimensional subspace. And as we get to this critical point, we are deforming this cloud. The connectome imposes its structure via the dynamics and changes this. And this is the object that we can actually now estimate, that describes the fluidity for real-world applications in the appropriate data. And in aging, this is the one that changes. Yeah? And in terms of dynamics, I'm coming back to your point. In terms of dynamics, actually, in the virtual brain, what we can actually do now, we can look at the EEG signals or the source signals or the corresponding fMRI. Here, this is the FCD for this particular behavior. What happens is when I actually look at the dynamics, it's composed of fixed points with varying stability, and there is a cascade of dynamics going from this part to that part. So you have a systematic stability change going from the posterior to the anterior. So you have essentially cascades flowing through this, and you see this actually when you region of interest, when you plot all the areas, you have an accumulation of cascades. You have these avalanches going through this. This translates into avalanches. This is coming from simulations. When you compute the cross correlations between areas, you can evolve that. Olaf Sporns called this edges and colleagues. Yeah? So you have edges, and you see increased correlations here. Do you see the spikes? And those spikes correspond actually to the squares in the functional connectivity dynamics, yeah? Which is actually fantastic. Yeah? So we are getting a feeling for what is actually happening in there. And if you test this in the mouse, we put the mouse into the scanner, bold signal, you see the same accumulation here and here, the spikes corresponding to the same spikes, squares in the FCD. Well, this is data from Petra Ritter's lab, where you have simultaneous EEG and fMRI. This empirical data, human, yeah, cascades that you can rediscover in the bold signal, and then corresponding beautifully to these things. So this gives you a feeling for what resting state dynamics does, well, how you can quantify it, and actually, just as a pointer, now it's being used by a larger consortium in Europe called the Virtual Brain Twin to actually start quantifying changes in schizophrenia. Look it up, please, if you're interested. And there's going to be, so some experts here in the room that have contributed to this over the years, and some further reading. Space, are you here somewhere? They're going to be, Space is there, Jan is over there, so we'll find them here at the conference at the time. And very quickly I have 3 minutes on my clock, yeah? For epilepsy, following situation, epilepsy, prototypical dynamic brain activity in disease. Yeah? What is the geometry of the manifold there? Yeah? Here you have 2 examples, empirical data, DC recordings, which are very rare. Yeah? So intracranial, typically you record with AC. Yeah? So here you have 3 types of seizures. Let's look at this one because this is one of the most common types. What you see here in the DC, you have a phase line, you have a phase jump, a baseline jump, bump, fast discharges, zzz, slowing down, and then suddenly it stops. You have a spike wave complex that emerges, and then the seizure stopped. Yeah, but it slows down. This intermittency between the spikes becomes larger. Yeah, in AC. This is what it looks like. Here you have a different onset. Not fast, but constant behavior, going up, amplitude growing, and then slowing down, amplitude going down. Here, same thing. These are actually in the, this here is a bifurcation onset, and this is bifurcation offset. This is how we can describe these objects, actually. This has been done Here you have a simulated time series. Think of this as a seizure, pre-ictal, seizure onset, seizure offset. The question is, how do I get from the non-oscillatory regime to the oscillatory regime? It must be a bifurcation, because something changes in the topology. So, but if there is a bifurcation, there must be something that is controlling this, yeah? And we talk about a slow variable. And you can actually show mathematically that you must describe it by a so-called fast, slow dynamics, where there is a slow variable generally controlling the onset. Then you will go through this oscillatory behavior, and then you have the offset. Mathematically, you go between rest and spiking, rest and spiking. And here, mathematically, it translates actually into a three-dimensional space, where you have, this is a spiral, a manifold, fast discharges. You have an onset bifurcation that gets you here, an offset bifurcation that gets you here, and you have a resting part of the manifold. This is the geometry of epilepsy. Yeah? And all the differences between the seizures are the different types of bifurcations that you can have, because there is a finite number of how you can go through bifurcations. Recorded data, mouse in tuto, hippocampus. Yeah? This here is extracellular potassium, which is a key candidate for one of the key candidates for the slow dynamics, fast discharges. Let's zoom in here. This is a little bit what you saw earlier. Baseline jump, bzzzt, slowing down, exit bifurcation. Yeah? And if you reconstruct the manifold, this is what it looks like. The resting state dynamics, yeah. I'm actually done. Thank you, Joanna. So you can actually decompose it into the different types of bifurcations, the ones we discussed, and build a taxonomy based on this type of seizures and extract it from the data, because each bifurcation has different behaviors. In real-world applications, it's being used in a clinical trial. You had this on your slides, in epilepsy, systematically exploited in the case of whole brain modeling. Look it up if you're interested. In terms of mathematics, this is literature I refer you to. Paul, are you here somewhere? Paul? No, no, he's coming only tomorrow, but he's going to be available in Borana. They're going to be here also. These are our epilepsy experts in the house. Many of us will be here, and in particular for the Koreans, local expert. I see Sora is here. She's here and has spent her postdoctoral fellowship with us, but she's an expert in the virtual brain dynamics. She's here in Seoul. Yeah. All of us from Brno, Jan, all of them are more Marseille trained. We will be here at the eBrains booth available. Yeah? And thank you. Yeah?
Wonderful, Viktor. This was really an inspiring talk, even seeing it for the second time. I invite you, if you didn't follow everything, you can come again next year if we are still here. Because this is really pushing the field in a new direction. And I invite maybe now to make just a quick question while Michael sets up before I introduce. And are there any comments, questions someone wants to make? Or we leave everything for the panel discussion? I can bring the microphone.
She wants to say something.
You, Danielle. Come on.
Thank you, and thank you for such a wonderful introduction into the geometry of dynamical systems. And one thing that I often wonder is, what is the range of different ways in which we typically construct a manifold, right? We talked about how you can go from this sphere at the end, this kind of spherical conformation, to more of these different cascading visualizations, but yeah, can you speak on the different shapes that manifolds may take and how we define them?
I can actually tell you how it's happening in the model from a modeling perspective. There we have it under full control. In real world, this has to be mimicked by different behaviors. For instance, the aging, there we know very well that most typical change on the structural level is the interhemispheric connectivity, which is actually very, very a robust phenomenon how the connectivity changes. Yeah? And this is actually mimicking very beautifully the changes in the fluidity that you observe there. Yeah? And what we see from the model is that the connectivity changes change the shape of the manifold. The manifold, we don't know yet exactly. Most likely the subspace of the manifold is somewhere between 5 to 12 dimensions. And when we are trying to characterize the shape, and this is what you were asking for, it's difficult to characterize it, such a manifold, so 5 to 12 dimensions. We can typically project it in 2 or 3 dimensions, yeah, and can give you a visual impression. We see that the manifold is very likely connected, yeah, and very likely there is a dynamics often coming from the posterior running through the manifold, which results in this fluidity changes that we saw there. When there are 2 ways of how the manifold can change. It can change its geometry under H, for instance, yeah, or it can change the flow on it. The dynamics may become more stable, more rigid in individual areas, while the geometry, the shape of the manifold, does not change. We don't know yet what is happening. There may be also combinations of this, but this is very important actually if you then want to perform inference and extract some of the underlying causal features. What exactly it is, we do not know. Yeah, to be done.
Well, very interesting to finish, and maybe we'll leave this for the panel discussion. Thank you so much, Viktor. You're really an inspiration for the field, and thank you.